So we're going to talk about domes, and we're going to talk about one of the largest and possibly one of the most famous domes in the world here in the UK. So in London, St Paul's Cathedral. It's a very large cathedral and it's right in the centre of London, and it has this really imposing dome, one of the biggest in the world. Diameter is 34 metres. The question becomes, how do you build the correct shape of dome so that it will sit under its own weight without supports, without masts? How do you actually create that? And that's a maths problem. So that's what we're going to figure out. The Great Fire of London, 1666, had just happened, and St Paul's was really badly damaged, and they wanted to rebuild this grand cathedral. Christopher Wren, very famous architect of the time, he was given the task of rebuilding this cathedral, and he wanted this big dome to kind of be the centerpiece of the cathedral. And at the time, he was really good friends with a famous physicist, Robert Hooke, and they kind of worked together to try and think about how can we have the largest dome possible that doesn't need any support. And because Robert Hooke was a physicist and a mathematician, he thought about this mathematically. And his amazing insight was to actually basically use nature to help us figure this out. So what he did was, I think he used a chain, but it's the same with a piece of string. And you just hold your two ends, like so they're level, so my hands are about level. And then you just let it form its shape. So this forms a sort of U shape, kind of looks like a parabola or an x squared graph, perhaps. And this is actually sort of, well, it's nature being lazy. It's the easiest way to describe it, because what's happening here is it's forming the shape that minimizes the energy of the string. So the potential energy from gravity pulling it down is minimized in this shape. So, and if I move my hands, it will obviously adjust its shape, still forming this kind of U shape. And Hooke's idea was to say, well, this is forming to minimize the energy. So if we flip it up, because when it was hanging, it was minimizing its energy. And the way it was doing that is by spreading out the weight as much as possible. So suddenly when you flip it upside down, you've got your dome where your weight is spread out as much as possible. And so that is going to help you to build the biggest possible dome you can, basically using nature as like a guide or a blueprint of how to do this. And this is what they did. So if you actually look at the original plans for St Paul's, or even the drawings of the building itself, it actually uses this idea and this shape. So the outer dome is a very big hemisphere. This is 34 meters in diameter, right across the bottom here. And then this kind of then comes down a bit. Down here is the inner dome, which is also a hemisphere like this. And this one's a little bit smaller, so it doesn't quite go to the edge. The inside one is 31 meters. So when you're inside St Paul's, you can look up and you can see all the beautiful artwork on the ceiling. That's the inner dome, not the outer one that you can see from outside. They're two separate domes. And the inner one is a little bit smaller, 3 meters less across. The sphere and sort of the perfection of it and the symmetry has symbolic meaning. So that was why these had to be spherical. This is kind of what Wren was told. But of course, he wanted to make it strong, make it, use maths to help us build this thing. So what they did was, on the inside bit in here, was actually create a third dome. And this is the shape of the hanging chain, or the shape of my piece of string. So this thing in here is actually what's bearing all of the load. So you have these kind of spherical shells on the outside, and all of the weight is actually supported by the hanging string or the hanging chain shape in the middle.
That's doing the business.
Yeah, that's the one that's actually supporting the dome.
Looks like the Star Trek symbol there.
Yeah, I'm not sure it's quite this pointy, but it's definitely not a hemisphere. As we saw when I was hanging it, it wasn't a sphere. It was very much more like a U shape. So this is supporting all of the weight. Now, they figured this out. So this was the idea, like literally Hooke did these experiments, was like, this is the shape we need to build. Now, the only problem they had was this was in the 1660s, 1670s. And to actually know this shape, this hanging chain shape, you need an area of maths called calculus of variations. And that was not discovered or invented until the 1750s, 100 years later. With these new techniques, this calculus of variations, as it was called, which was actually worked on mainly by Euler and Lagrange, so two very big name mathematicians of the 1700s. So with calculus of variations, you can show the exact shape that this needs to be. and it's something called a catenary. This is the exact shape of our hanging string, but the dome itself in St. Paul's is like a very good approximation of this. But that's nothing against Hook and Wren. They just didn't yet have the mathematical tools they needed to get the exact shape. So they were basing it almost on like an approximation and an experiment.
So they literally kind of like traced something like...
More or less, yeah. Like, it's really interesting. You can actually look at the original drawings and you can see that they are literally just like kind of sketching what the shape should be based on the shape of a hanging chain. So even though they didn't have the right mathematical tools, they had the insight to actually put them to work. And it obviously works. The dome is still there today. So now that we do have the tools, the shape itself is something called a cosh curve, or a hyperbolic cosine. So with the full tools of calculus of variations, you can set this problem up, hanging chain, I want to minimize energy, and your answer is this cosh curve. So then what we want to know is, well, what on earth is a cosh curve? And that's when I'm going to need more paper. Cosh of x. So this is the actual shape we want for the catenary, for the perfect dome shape. The cosh function is an exponential function. So the starting point actually here to figure out what's going on with cosh is to consider the function e to the x. So e to the x is a function which has an expansion, which is 1 plus x squared divided by 2 factorial plus x cubed over 3 factorial plus dot dot dot. And the graph of this function goes through 1, like so, at 0, and then it decreases. Never quite gets to 0, and then this bit increases. So this would be y equals e to the x. So as you can see, as x gets bigger, you're just adding together lots and lots of powers of x, so the thing's going to grow really quickly. This is exponential growth. Now, the cosh term is very similar to the exponential, but what you say is, I just want the even terms in this sum. So I want x to the 0, which is 1. I want x squared. I want x to the 4. I want x to the 6. I'm just going to take the even powers of x, and let's see what happens. And that's basically how you define cosh. It's the even terms of your exponential. So you would write then cosh of x is 1 plus x squared, because of course 2 is even, plus x to the 4, because 4 is even, and we carry on in that way. You can also think about reflecting its graph. So when you have an even function, what that means is it's the same either side of the y-axis. So if we kind of take this bit of the graph, reflect it, this is basically the cosh curve, which is the nice dome shape and the nice hanging string shape that we had. This would be y equals cosh of x. Now, cosh comes from the even terms. Maybe you're thinking, well, what about the odd terms? And obviously we have a function for that. So if we do the odd terms, then that is going to be sine of x. Just like this is hyperbolic cos, hyperbolic sine. And this one is going to then be x, because that's to the power 1, x cubed plus x to the 5. So it's just all your odd powers. And sine of x, it's the same up here, but this one goes through 0. So it's a bit more like an x cubed graph. It's got that kind of kink, almost like S shape to it. And this one can be negative because you've got, if you sub in negative values of x, you're going to get minuses from the odd powers, whereas negative values of x up here give you positives. So cosh stays positive, but sine can go negative. So we have these two functions, and then there's actually a shorthand way that you can write cosh as well using the exponential formula, is you consider e to the minus x. So you just take your e to the x formula, but wherever there's an x, you plug in a minus x. So plus x, that becomes a minus. X squared, so minus 1 squared is just 1. So I still get plus x squared over 2 factorial. Then I'll get minus x cubed over 3 factorial, and I'll carry on. So the terms, the sign alternates when you plug in minus x. So now, if you take e to the minus x and e to the x, if we add them together, so we do e to the x plus e to the minus x, I'm going to add them together, and I'm going to divide by 2. Because I'm going to get 1 plus 1, and then when I divide by 2, leaves me with 1. I've got plus x and minus x. They disappear. I've then got 2 lots of the x squared term, but I've divided by 2. So I just get plus x squared 2 factorial. The cubic one here, it's got a negative. Here it's got a positive. They disappear. So it'll be no cubic term, x to the 4th, and then we carry on. And of course this is cosh of x.
The evens.
The even terms. Exactly as we defined it here, but now you can write it in this really nice shorthand formula. It's just e to the x plus e to the minus x divided by 2.
What's the variable here? If I want to go home and build a dome on my house, What's the, which is not as wide as St. Paul's Cathedral,
Yep.
what's the thing I need to change, like, to get my graph?
So if you are to draw the graph of cosh, so depending on how wide you want your dome, this is going to tell you the shape. So if your dome's really narrow, let's call it 5 meters, then you would go up here and you're going to get a very kind of wide, flat dome in that instance. Whereas if you're going to like St. Paul's, which let's say maybe that's all the way out to here, and that distance is your 34 meters, then you're getting this kind of bigger shape. So all of them follow the same graph. So the other thing that will change is the length of the string. And this comes up in the full calculus of variations way of solving the problem. You do have to input, my string is of this fixed length. So the solution does depend on the length of your string. So if I have my fixed length of string here, then I form this particular shape. But then if I say, right, well, I'm only going to have this bit of string and they're still that far apart, I've got a much shallower dome now. But no matter what length of string you have and how far apart my hands are, all of these shapes that are being formed are cosh curves. They are all hyperbolic cosine curves. You've just got a variable in there which is representing the fact that the length or the distance is changing.
So no matter what droop I'm seeing there in the string,
Yeah.
it is some variation of that same curve I'm
It's
seeing.
still a hyperbolic cos curve, yes. Yeah. In all of these situations, the answer is the cosh curve.
I'm just sort of seeing it at different zooms.
Exactly, yeah. So either at different zooms or you can, because if I put them really close together, now it's a very different shape, but that is still a cosh curve. You could still write down the actual formula. So the full formula will be cosh of something, where that something depends on the length of your string, depends on how far apart you are. So there are variables that you have to input to get the exact answer, but everything that comes out is this hyperbolic cosine function. Wren and Hooke cosh didn't exist until the 1760s, in fact. So it wasn't even a function. So they had no chance of knowing that this was the shape they needed to build this dome. So they just had to take like best guesses. And they kind of did this through almost knowing what it wasn't. So through their experiments with the hanging chains and the string, they knew it wasn't an x squared. So they were definitely sure it wasn't the parabola. So then they kind of tried, well, what's the next simplest thing I could have? Maybe it's a cubic. Maybe it's a y equals x cubed. So if we were to plot y equals x cubed, and we're just going to add 1 to it so that it goes through 1 instead of 0, just because cosh also goes through 1. If we were to draw y equals x cubed plus 1, it would look like that here, and then it would kind of go down like this. What Wren and Hooke did was they reflected it. So then we kind of extend it this way. So it is believed that the actual shape of this inner dome at St. Paul's is an x cubed curve. That is what we believe at the moment they actually base this on. And it's a really good approximation to the cosh curve. A cosh curve on top of this, it basically looks kind of the same, very similar at the start. It does eventually come through. And then what happens at really large values of x is, because the cosh is an exponential function, exponential functions will always beat polynomials. This is why exponential growth is such an issue and such a thing, because exponentials will eventually grow faster than a polynomial. So it will eventually beat the x cubed. So even though it sort of starts inside and then comes outside, eventually it comes back up here and becomes narrower because it grows faster. So the idea, the thing that clearly Wren and Hooke spotted was that, their drawing the red curve is based on their experiments with the string and the hanging chains, and they clearly spotted that the x cubed does a really good job of capturing that. And so we believe that that is actually what they used to build that inner dome at St. Paul's that's taking all of the weight, allowing such a big dome to actually exist.
This episode's been supported by KiwiCo, and today I'm making an infinity mirror from their Tinker crate. KiwiCo delivers all sorts of crates with different themes, different target ages. Just take a pic from their website, then find one on your doorstep every month. It's like Christmas all year round. Everything you're going to need is already in the box. Even the batteries are included when necessary. These are great for kids, including slightly bigger and older kids like me. It's a real learning experience. Sometimes I didn't even realise how clever this was until after I'd made the thing. gave me a bit of an insight into how things get made, actually. The address is there on the screen, kiwico.com/numberphile. That's going to get you 50% off your first month on any crate. kiwico.com with that /numberphile. And take a look at that. Love it. A KiwiCo subscription would make a great Christmas or birthday present.